Good evening, everyone. In today's class, we are going to start with the eighth chapter, that is gravitation. So, first, let us see what is gravitation. A force that exists among all the material objects in the universe is known as a gravitational force. So, if you have any two objects which are having some mass, then there will be a force between those two objects that is called what? That is called your gravitational force. Next, we have Newton's law of gravitation. What does it state? Newton's law of gravitation states that force between two objects, say m1 and m2 here, the force between two objects is directly proportional to the product of their masses and inversely proportional to the square of distance between them. So if I have to write in form of the formula, the force between the two objects is proportional to the product of their masses. So if I consider the mass as m1 here, and if I consider another mass to be m2, the force between these two objects is going to be proportional to the product of the masses m1 and m2 and inversely proportional to the square of distance between them, and also inversely proportional to the square of distance between them. That is, the distance between them, if I take as r, f will be proportional to 1 by r square. So I can write here f is going to be proportional to m1 m2 divided by r square. In order to remove the proportionality sign, I need to introduce a constant here. That constant here is going to be your gravitational constant g. So F is given by G multiplied by M1 M2 divided by R square, where G is your gravitational constant. So you can say from Newton's law of gravitation that force between two objects is directly proportional to the product of the masses and inversely proportional to the square of distance between them. Gravitational constant. It is represented by the letter capital G, and it has a constant value which is given by 6.673 into 10 to the power minus 11 Newton meter square per kg. So your SI unit for your gravitational constant, it is going to be what? It is just given here, the same thing you can take. It is Newton meter square per kg. Similarly, if I have to calculate the dimensional formula of your gravitational constant, I can calculate. What can I write your G as? G can I write as Fr square divided by M1 and M2. So this is nothing but Newton meter square per kg, right? Now, what will be the dimensional formula for Newton? For force, I can write force is equal to ma, so m l t to the power minus 2, this will be your Newton multiplied by m square. What will be your m here? Sorry, this is your r, so this will be your l, right? So this will be your l square divided by your kg, so again your m square you will be having. So what will be the dimensional formula for your gravitational constant? So the dimensional formula for gravitational constant is given by m to the power minus 1, L to the power 3, T to the power minus 2. So this will be the the dimensional formula for gravitational constant, which is capital G. Next, we'll solve a question on the same. The mass of the Earth is 6.6 into 10 to the power 24 kg. The distance between the Earth and the Sun is 1.5 into 10 to the power 11 meters. If the gravitational force between the two is 3.5 into 10 to the power 2 Newton, what is the mass of the Sun? So let me consider Earth over here. Let this be the Earth, and the Sun is over here. Let us consider the Sun is over here. Let m1 be the mass of the Earth, m2 be the mass of the Sun. They have given that mass of the earth is 6.6 into 10 to the power 24 kg. So I will be writing here m1 is equal to 6 into 10 to the power 24 kgs. Next, the distance between the earth and the sun. The distance between the earth and the sun I can take as r, which is given to be 1.5 into 10 to the power 11 meters. Next, the gravitational force, that is your F, between your earth and sun, that is given to be 3.5 into 10 to the power 2 Newton. F is also taken. What is the mass of the sun? Mass of the sun I have taken as m2. So m2, I can put the question. I know from the law of gravitation that force F is given by G m1 m2 divided by r square. Now here I need my m2. So if I need my m2, what will be the formula for m2? I can write your m2 as m2. Can it be written as F multiplied by r square divided by G multiplied by m1? So substituting your F, we will be getting 3.5 into 10 to the power 2 multiplied by 1.5 into 10 to the power 11 whole square divided by G. What is your G? G is a gravitational constant, 6.67 into 10 to the power minus 11 multiplied by m1, which is the mass of the earth, 6 into 10 to the power 24 kg. Upon solving, we will be getting the value of m2. I will be writing the direct answer over here. So m2 approximately we will be getting around 2 into 10 to the power 10 kgs. So this is going to be the mass of the sun. I hope it is clear. Can we move on to the next topic? So the next topic we have is, we have seen what is gravitational constant G, which is represented by capital G, and we had a value for that, which is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Now, what is acceleration due to gravity? This is also a constant for Earth. This is for the Earth. So G is given as 9.8 meter per second square. So, the acceleration of a free falling body is known as acceleration due to gravity. So, if there is any body that is freely falling, the acceleration of that body is known as acceleration due to gravity. Here we have another topic, that is weight of the body. What is your weight of the body? The force of the gravitational attraction of Earth on the body is called the weight of the body, and this weight always acts in the downward direction. So from Newton's second law, I know that F is equal to ma. So I can write F, which is equal to ma. So if a body is falling or is in a free fall, then acceleration can be taken as acceleration due to gravity, which is your G. So I can write A as G. When I write A as G, the force is called what? The force is called weight. So F I can write as W will be equal to M into G. So what is your weight? Weight is given as M into G, where M is the mass of the body and G is the acceleration due to gravity. Now we will consider, or we will derive a relation between acceleration due to gravity and the gravitational constant G. So basically your small g and your capital G. For that, we will be sorry. For that, we will be considering an object or a ball at some height h from the earth. So this is the earth, r is the radius of the earth, h is the height of the ball. Let us consider a body of mass m, that is the ball here, near the earth's surface, falling with an acceleration due to gravity g, and let the radius of the earth be very much greater than the height. So you can consider that the height is negligible here. So the height is negligible. Let r, the capital R, be the radius of the earth and capital M be the mass of the earth. So from the Newton's second law, what can I tell from Newton's second law? I know that the force is given as M into A. Is that correct? Yes. If a body is falling with an acceleration due to gravity, which is g, can I take that F will be equal to mg? F will be equal to mg. Also, from the law of gravitation, what do I know F as? I know that the force between two objects, that is going to be equal to g m1 m2 divided by r square. Yes, or here I can take, let m be the mass of the ball, okay, and the bigger m be the mass of the earth. So I can write here, instead of m1 and m2, I will be writing here capital M and small m. So F is equal to mg, F is equal to gmm by r square. Here one is capital, one is small. The capital is the mass of the earth, mass of the ball is small m. So can I take F is equal to F, because both are the force and both should be equal. So from, I can take this as equation number 1, this as equation number 2. From 1 and 2, what can I write? Can I write that mg will be equal to gmm divided by r square. So I can cancel this small m and small m to get the value of g, which is small g is given by capital G multiplied by m divided by r square. So g here is the acceleration due to gravity of the earth, which is given by capital G, which is the gravitational constant, multiplied by m, which is the mass of the earth, and your r, I have taken capital, so you can also take capital R. Is this clear? Okay. So this was the relation between the acceleration due to gravity and gravitational constant g. Variation of g with height. Here I told you that let the radius be very very large or the h is negligible, right? We are not considering your h over here. Now what if the h is little large? In that case, what will be your g, or how will your g vary? Okay, for that we have a direct formula. So variation of g, which is given by g dash, it is given by g multiplied by 1 minus 2h divided by r. So at the height h, so let me take the same diagram. Where was it? This one, right? Yes. Yes. So variation of g with some height. If any body is there which is falling from a height h from the earth's surface, then the gravitational acceleration, or you can tell acceleration due to gravity g dash at that height, will be given by g multiplied by 1 minus 2h divided by r, where r is the radius and h is the height. Is that clear? Yes? Okay. Now, let us move on to the next question over here. If the weight of a body on Earth is 12 newtons, its weight on the moon will be acceleration due to gravity on the moon is already given. So, I will be writing here on Earth, and here I will be writing on. Okay. Now, weight of the body is given. So, what is your weight given by weight is mg, correct? So, weight is given as 12 Newton on the earth and m is not given. So, m I will be keeping as it is, which is the mass of the body. And what is your g? G is 9.8, right? Meter per second square. Now, what will be your mass? Mass can I take as 12 divided by 9.8. So, m I will be getting around 1 point, say, 22. Is that what I will be getting? Yes. So, the mass of the body I am getting as 1.22. Now, we will go to the moon. So on the moon, what will be the weight? So this is on the earth. So this is GE on the moon, right? Now, on the moon, what will be the weight? It is mass into acceleration due to gravity of the moon. Now, what are they asking? The weight of the moon will be. So Wm, they are asking, m you already know, which is 1.22 multiplied by gm is the acceleration due to gravity on the moon, which they have given as 1.66. So you just need to multiply them both. So if you multiply them both, what is the answer you will be getting? The answer you will be getting is around 2 newtons approximately. So this is a choice question. On A will be your correct option. So let me just move this a bit this side so it is more clear. Now it's clear, right? It's okay. Before I go to the next topic, that is Kepler's law, I want to discuss about a shape. What is that? It is called ellipse. Okay. Now, ellipse is somewhat like a flattened out egg, right? Or horizontal egg shape or a oval shape you can take. So similar to your circle, even this will be having a center. Okay, it will be having a center. You can observe that in circle, the radius will be the same, meaning that the distance from the center to any point on the circle will be, the distance will be the same. But in ellipse, there will be two radius, meaning that there will be two distances. One distance which is the farthest from the center and one more which is the shortest from the center. So I can tell that a line which passes through the center and the longest side. So this is the longest diameter I can tell, right? Of the ellipse. This is the shortest diameter I can tell. This one. So the longest diameter is called major axis and the smallest diameter is called your minor axis. And the distance between the center and the vertex here, this distance is taken as A. And distance between this point and the shortest point, that is taken as B. So let me take over here. So this is taken as, so total distance from here to here, it is going to be 2b. Total distance from here to here, it is going to be your 2a. So I can tell 2a is the length of the major axis. Major axis because it is the largest. Minor axis, which is from here to here, it is b. From here to here, it is also b. So the total distance, it is going to be 2b. So this is what you have to know about the ellipse. There are two more things which you have to know, that is your focus. So there will be 2 points or 2 points on either side of the center, which is called the focus of the ellipse. Okay, fine. Now we will start with Kepler's laws. Kepler's first law. Kepler's first law states that all the planets move around the sun in elliptical orbits with sun at one of the foci. So you can assume that the planets revolve around the sun in which orbits? In elliptical orbits, not circular orbits. We assume it to be circular, but actually it is your elliptical orbit. And how is your sun? Sun is one of the foci. It can be here or it can be here also. As you can see from this side, that the ellipse has two focus, right? Foci. So this is about your first law. Second law states that planet sweeps equal areas in equal interval of time. What does it mean? Now let us consider a time interval of say 5 seconds or 10 seconds. So in 10 seconds, let the object or let the planet move from this point to this point. And let us consider again 10 seconds at any other position, say from here to here. So in the same interval, if the planet travels from here to here and here to here, if I join those distances with the center, I will be getting like a triangular form which I have shaded with pink color. Now, the second law states that the area swept over here will be equal in equal intervals of time. So here the area 1 will be equal to area 2. This is your second law. The third law states that the square of the orbit, or you can tell the square of the time period of the planet, is proportional to the cube of orbit's semi-major axis. So if I consider the semi-major axis to be A and the time period to be T, time period is the time taken by the planet to go one round around the sun. Okay, that is your time period. So if T is the time period and A is the semi major axis, I can tell that T square will be proportional to AQ. So these are three Kepler's laws. Are they clear? Let me discuss them one more time. So Kepler's first law states that all planets move around the sun in elliptical orbits with sun at one of the foci. The second law states that the planet sweeps equal areas in equal intervals of time. The third law states that the square of orbital time period of the planet is proportional to the cube of orbit's semi-major axis. Once we have completed with Kepler's law, we can start solving problems on the same. So let us consider question number 1. The mean distance of Earth of mass 6.3 into 10 to the power 24 kg from the Sun is 150 million kilometers. Find the aerial velocity. So aerial velocity is being asked in the question. So let me write down what is the aerial velocity first, then I will be solving the same. So aerial velocity is given by, aerial means area, so you can consider pi r square divided by t. This is the formula for aerial velocity. Now, in the question, the mean distance of Earth of mass of Earth is given from the sun, which is 150 million kilometers. So only thing we are concerned with is the distance. So R is given as how much? 150 million kilometers. So million has how many zeros? Million has 6 zeros, right? So 10 to the power 6 multiplied by The distance every time it should be in which unit? Kilometers, meters, feet. It should be in meters. So kilometers to meters, if I have to convert, I have to multiply by 1000. So can I write as 10 to the power 3? Yes, I can write as 10 to the power 3. So I will be substituting the same. Pi is 3.14 multiplied by r square. R is 150 multiplied by 10 to the power 9 whole square divided by t. What is your t? T is the time period, right? What is the time period? What is the time the earth takes to go around the sun? 365 days. But the time should be in which unit? It should be in seconds, right? So I can convert days into seconds. So I can write 365 days multiplied by 24. Okay, each day has 24 hours, and in 24 hours, how many minutes are there? 60 minutes are there. So multiplied by 60, multiplied by in 60, in minute, how many seconds are there? 60. So again 60. So upon solving, I will be getting the aerial velocity, which comes out to be 2.24 into 10 to the power 15 meter square per second. This is going to be the aerial velocity of Earth. Let us move on to the question number 2. Time period of Jupiter is 11.6 years. Time of one complete revolution. How far is Jupiter from the sun if the distance between the sun and Jupiter is 1.5 into 10 to the power 11 meters? Okay, so let me write down whatever is given in the question. So they have given time period of Jupiter. So I can take Tj of Jupiter. It is given as 11.6 years. Next, they have given the radius of the Earth, right? Basically, the distance of the Sun and the Jupiter is given. How far is Jupiter from the Sun? Distance, sorry, this is Earth and the Sun, between Sun and Earth. Okay, this is Sun and Earth. It is not Sun and Jupiter. Just make a correction over there. So I can write that the radius or the distance between the Sun and the Earth, I can take RE to be equal to 1.5 into 10 to the power 11 meters. So the time period of the Jupiter is given. The distance between the Earth and Sun is given. What they're asking the distance of the Earth from the Sun. Okay, how far is Jupiter? Oh, sorry, they're asking how far is Jupiter from the Sun. So basically, RJ is the question mark, right? What is the time period of the Earth? 1 year, right? Basically, it takes 1 year to go from one point to another point. That is your time period. So I know the time period, I know the radius. So can I tell that here Tj square will be equal to Re cube, and also over here Te square will be equal to Rj square. So here, sorry, this will be Rj, here it will be R. Yes, because time period square will be equal to the cube of the semi-major axis. Right. Now, if I take the same ratio, I can write that Tj square divided by Te square. This should be equal to Rj, or I can take like this, big R I have taken. So I can take your Rj Re whole cube. So I want Rj. So Rj cube is going to be equal to 1.5 into 10 to the power 11, right? Multiplied by 11.6 whole square divided by 1. Now I just want my Rj, right? That is the distance between the Jupiter and the Sun. So if I want to do that, I need to take cube root on both the sides. Upon taking cube roots, I will be getting, or I should be getting, the answer as 7.68 into 10 to the power 11 meters. So this will be the distance between the Jupiter and the Sun. Let me consider one more problem. A and B are two satellites revolving around the Earth in circular orbits having time period 8 hours and 1 hour respectively. The ratio of their radius of orbits are. Okay, we have to find the radius of the orbit over here. So let me write down whatever is given. Let me consider the time period of satellite A to be 8 hours. That is what they have given. Time period of satellite B is how much? It is 1 hour. Let us consider the radius to be RA and radius to be RB. What they are asking in the question? They are asking the ratio of their radiuses. Okay, they are asking the sorry, ratio of the radius. So basically they are asking what is Ra divided by Rb. This is the question. So I know that Ta whole square will be equal to Ra whole cube. Also Tb whole square should be equal to Rb whole cube. Is that correct? Yes. Now what will be Ta and Tb? I need to find out, right? So Ta and Tb is already given. So here I can take 8 divided by 1. This should be equal to Ra. Do you know what is your Ra and Rb? Ra and Rb we don't know. So Ra and Rb we will keep it as it is. It is cube. So what I will do is I will take cube root. So here I can write 1 by 3. Can I write like this? This is squared. So I can write 2 by 3. So Ra divided by Rb is going to be equal to 2 divided by 1 uh, to the power whole to the power 2. So it will be 4 by 1. So what you can write, Ra by Rb, the ratio is 4 by 1. Or you can also write as 4 is to